Okay, so good afternoon. As said, I'm Alan Beccati from the member of the Silva team in Bremen, and we are partnering the de.NBI projects. And I'm here to tell you how we are leveraging the de.NBI cloud to provide computing power for the SILVAng system. So to that extent, I will give you a brief introduction to the SILVAng platform and describe its system architecture. And from that architecture point of view, we will match which requirements are needed for running the platform and which tools the de.NBI cloud provides for satisfying these requirements. Then I will tell you how I set up this, the whole infrastructure and provide some statistics of the last 2 months of running on the cloud. So what is SILVAng? It's a next generation sequencing analysis platform, and it's based on the ribosomal RNA gene. It is provided as a web application, so basically it's a software as a service that we provide on top of the de.NBI cloud in terms of cloud terms. It has a peculiarity that it uses the Silva databases, because the Silva project also has a core asset in providing the Silva sequence database and the taxonomies. And so the analysis service uses, of course, these taxonomies for providing the results. The results available to the scientist are in the form of tables, text file, graphs, and sequences that the user can download after having the analysis. So the basic workflow is you go to the website, upload your sequence data for the analysis, click on the run and process, and after a while, you get your results for download directly. So basic, easy-to-use platform for the scientist. Well, the user just sees a web server, so a web application. Behind it, we have this kind of infrastructure where a compute cluster is needed to do the compute power for the processing. On the head node of the computer cluster, there is a component called dispatcher that periodically checks on the web server if new projects need to be computed, and in that case, downloads the data, submit the relevant jobs to the compute cluster, and after processing is done, packages the results back to the server for the user to download. So it's a completely automated platform that runs on this system. We also have a local storage system in the cloud where we store our databases that are required for the computation. So what we need is to reproduce this architecture completely into the de.NBI cloud. Before that, I want to tell you how the analysis platform itself works. It's basically a workflow consisting of several modules, and each module performs one step of the analysis. So there are the init and import modules, which create a local database where all the sequences are stored, and the import will load all the FASTA data from the user into the database. We use basically a local database to be able to perform analysis on the results and statistics afterwards. So after the processing is done, on the database we can run the analysis and the statistics tools. Then there is the align and quality steps where the user sequences get aligned against the Silva seed to provide the analysis, and some quality check is done to discard sequences that do not pass the quality criteria for the analysis. Then there is a dereplicate and cluster module where the sequences are dereplicated and clustered to obtain only the cluster references, which allows us to use less computing power because we do the next classification step with BLAST only on the cluster references. The next step is the OTU map, where you find the operational taxonomy unit across the samples, which basically is equivalent to a global clustering of the whole data set. And yeah, because basically the user can upload one file for each sample, and the global clustering is across all the samples that the user provided for the analysis. Then we have stats, rarefaction, and taxplot modules that are actually computing the graphs and the charts and the files for the user to download the results. Finally, the export module will save the results from the database to the hard drive to get uploaded to the server. So this is basically all the steps of the platform. Why I presented the steps and why do we need a cluster behind that? Well, the cluster is advantageous when we can compute things concurrently. So basically, for the steps I presented, we have align, quality, and classify that are highly parallelizable. And in theory, you can run independently a module on that for each sequence. Actually, we package some sequences together to avoid some overhead. But that's the most advantageous steps in the usage of a cluster. Then the import, the replicate, cluster, and rarefaction modules can be parallelized only at sample level. So for each samples that the user provided, we can run on a computer node one of these modules to process the data. And finally, there are steps that are not parallel at all, and only one compute cluster will be, one compute node will be used for these steps for a single project. Okay, so let's have a look at the requirements. As I told you, we need an SGA compute cluster to run the analysis. We need a MySQL database to store the intermediate results of the analysis. We need to install local software accessible from the cluster, basically the pipeline itself, the job dispatcher, and the bioinformatics tools that are used by the platform. And we want to have monitoring of the resource in the cluster and notification in case of troubles. So let's start with the local software, local storage. We have used OpenStack volumes that are basically storage units that you can define in the OpenStack and attach in any of your instances in the cloud. So this is basically providing you storage space where we can compile and install all the required software tools. We have two volumes, one for the software itself and one for the computing workspace, so where we store the processing data and the user data. I don't have really a best practice for that because we used a single instance in the cloud, connected the volumes to that, and installed all the tools required for compiling the software on that instance to avoid having on the production server all the tools also installed. What is nice from this volume is that when they are ready, all your software is installed, you can detach them from this instance and attach them to the cluster afterwards. Now let's have a look at the SGA cluster. So setting up a compute cluster is quite a demanding task. You have to configure, set up the instances, run all of them, and configure them to build the cluster. The very good news is that there is the tool bbgrid available for that. You can use that tool, as Peter told, to provide your infrastructure as code. So that the only thing you have to do is take a YAML file, configuration file template, and with this template you specify how your cluster should look like. In the YAML file you can specify a master node, which kind of master node you want, different type of slaves in the cluster altogether, which volumes you want to use for the software that is deployed on the cluster, and they can get automatically exported and as NFS shares available to the whole cluster. So this is a very practical tool that you can use for setting up your cluster in the cloud. An advantage is that also monitoring has been set up automatically by the tool using Ganglia. Okay, so actually no tool is perfect. bbgrid is a very good one, but we had some difficulties in using that. In this case, for when using advanced topics for the cloud configuration, like server groups. Server groups, in this case, for example, the anti-affinity server group allows you to distribute your instances on different hypervisors, so to optimize the computer power available to your system. What was the problem? I think there was a concurrency problem. When you create the instance were created too fast, too quickly, the OpenStack didn't respect the the server group, the anti-affinity policy itself. So what was the good news? The good news is that BBGrid is an open source tool, so we had access to the source code. Fixed that, we're introducing a delay into the creation of the instances, and rerun the configuration with that modification, which solved basically the problem. Another issue on BBGrid was that at the time of when we were using it, it didn't provide any further customization. So you could get a standardized cluster. Oh, sorry. I need a bit of water. So as I said, you could get only a standard version of the cluster, but we required several more configuration on each node to be performed. And in that case, we have to resort to manual configuration. For example, on the master node, we have to install the dispatcher, and we did it manually, logging into the master and configuring it for execution. Some other things that could be run on each of the nodes, we leverage the cluster itself for doing that. So we provide the bash configuration script and run it on the cluster so that the cluster itself configure its own nodes. And the very good news is that now and tomorrow you will see it, I look forward to it, there is a new support for Ansible scripts that can be added to BBGrid to perform also these custom configuration steps, which we will definitely use. So the tool from my side is definitely worth a recommendation. If you need to set up the cluster, use it because it's worth it. Last but not least, we had to configure a local MySQL database. Again, not good practice because I did this manually because it's a single server. And as you know, as you have heard, the configuration tools that can automate that, like Ansible, Terraform, or similar tools, are good to use when you have many more machines. But for a single server, still a manual configuration can be the best option. One trick that I had to apply is that, and you have to be aware of, is when you configure in OpenStack, you use directly the infrastructure, and you have to be aware that the networking is a bit tricky. So there are security groups in OpenStack where your machine are located, and in this case, BBGrid created its own security group, and the MySQL server was located outside of the group, so in another security group, and you have to configure manually the firewall rules between the machines to provide access to them. And of course, the MySQL database is not included in the monitoring because it's not part of the cluster itself. So looking back at the system architecture, as I defined, practically we managed to recreate everything behind the web server on the de.NBI cloud using most of the de.NBI cloud tools that are provided. Let's have a look at the requirements we had and how they got matched by using the de.NBI cloud. So the SGA compute cluster was set up using BBGrid, requirement perfectly matched. MySQL database, again, a single instance configured manually, but we have it. Local software, we used the volumes for that, the OpenStack volumes. And for monitoring, there is the Ganglia instance set up automatically by BBGrid. The only requirement it is not met, actually, is the notification, because there is no external tool to the cluster that can notify you if something goes wrong in the cluster. So, but for that, actually, the admins in Bielefeld are very active and reactive to problems that has been occurred, and they send out notification mails. So we can also live with that without a problem that we are notified also, even if not automatically, that something is not going wrong and the service is maybe not available. Okay, to conclude, a bit of user statistics. On the left, you can see the profile, the cluster profile of a single project that has been run. And you can very well notice that, as I told you, the very high concurrency steps of the pipeline are configured to use the complete amount of resources available on the cluster. But there are in between and in the end the other steps which does not allow concurrency, that take up running time but cannot be more parallelized than that. To cope with this, we allow 4 projects to run concurrently on the cluster and hope that they are interleaved so that the cluster will be used most of the time at full capacity. For the last 2 months, we had in August, you can see on the right the statistic for August, where we had almost 200 small projects and a few larger projects that used more computer resources. Actually, the very large project we still run at the infrastructure of the MPE that require manual execution, because these are smaller projects which can be run automatically, and we are sure that they run without issues. For larger projects involving tens of millions of sequences, we still process them manually step by step and check the results to ensure that the scientist gets the correct results. So on average, we have about 200 executions per month in the last 2 months. Okay, and that's all from my side. Thank you for listening.